Hey everybody. Okay, I'm back. It's been a long delay. I've been busy. As you can see, I have a new place I live. And also, my friend bought me a cool new sign. So today we're gonna do some summation. So we've already got the test code written for this. See, I've been really busy. What have I been? Let me pull up my channel here. Okay. Still pulling up my channel. Here we go. Yeah, I moved. I've been private tutoring for a while, and on top of that, I've been reading some of the latest research being done, specifically on GPU optimizations. So that's for the Volta architecture, which is similar to the Turing 20 series. So soon I'm going to be targeting that. So we got some work in the pipelines done. Okay, so also what's happened is my computer, it broke. It stopped working. So the internet just completely broke on Windows, so I had to reinstall it. Because of that, I've got to update my toolkit here. I'm on CUDA 12.1. So I'll update that. We don't need this because it's already up here. I was looking around at this a little beforehand. Yeah, that should be good for now. I'll zoom in a little bit. Okay. Let me make sure this builds right now. It's where we left off. All right, oh, you know what? Actually, what are we on? We're on MNIST right now. So that's number 5. Okay, so 05 tab, get that going, run. All right, building. There's something else I want to do. I want to switch to Ninja. Ninja by default, it'll build on all the cores, and it compiles a little bit faster. It goes through all the projects. Okay, so we have an error here. Util write to CSV. Unresolved external symbol, and same thing here. Oh, I looked up how to get rid of this warning. Let's fix the error first, though. Okay, so whatever file this is in is probably just not. Whatever we have it defined in, it's probably just not building. File writer, neural net. Okay, so when we're under our MNIST program, it's not there. Okay, it's not here either. I had it commented out. Probably for compatibility for another project, but we'll just worry about MNIST for now. Okay, compiling. I think I have a faster way to do this. All right, we got it building. Could not open file. I don't have a saves folder here. Okay, put the saves folder in, and then this should be part of the repo. I took it off. So instead of removing the whole directory, I'll just ignore all the files in it like this. See if it shows up now. No, it doesn't show up. I want to have it blank in part of the repo. So it's blank right now. Git add all. Git status, so it's there. It's not showing up. Git commit message, okay, fixed. MNIST compilation error. And updated cmake list.txt to the latest CUDA install. All right, we'll just push it. I've used Ninja at work before on Linux, so at some point I'm going to try it on Windows. I don't know why it's not showing the saves folder here. Let's we'll worry about that later. Okay, file writer's done. Let's get back to, I'll do all this housekeeping stuff at the end of the stream so we can get to the juicy stuff faster. Okay, I'm trying to remember where all this is. So we have MNIST, test, reduce test, algo, reduce. Okay, so here's our reduce header. Here's our test that we already wrote, and we have reduce included in it. Reduce. Okay, this is a kernel, so we can call float to half. All right, let's get started on our reduce function. So first off, if our reduce is greater than size or equal to it, we can just return out of this. This should be a void because we're just gonna sum it. We're gonna reduce in place. So let's do that. Sum in place. We'll rename it to that. Okay, so what we have to do first is however big our array is, we're gonna sum all of the elements in it all to the very first element. So what we're gonna do is say we have 10 elements. We want to get it to the power of 2 that's highest that fits within it. So that would be 8. So what we're gonna do is we're take the last 2 of it and we're gonna add those to the first 2. So then we'll have 8 elements, a power of 2, and then we'll split it in half and we'll add the last 4 to the first 4, then we'll add the last 2 to the first 2, and then the last one to the first one. And that'll get it done for us. So I looked online, I found there's a cool little instruction where it counts the leading zeros that you have in your number. And what that'll do, so you have a 32-bit int. if you just take 31 minus the leading zeros, that'll give you the log base 2 of the number. And then you can just take the log, raise it to the power 2, because it'll be a whole number. It rounds down, it's an integer log. And then you'll raise that to the power of 2, and then you'll get the number. You'll get the highest power 2 that fits in it. Okay, so I have in my notes here that we'll name it log 2 of size equals 31 minus CLZ of size. And I don't know what CLZ stands for. But this will give us our log 2 here. So also in my notes, so we have to have our cooperative groups. That's a terrible autocomplete. Grid group G, we'll name it this grid. Okay. So now that we have the log, we just take the power of 2, and a fast way to do that is we could just take 1 and bit shift it over. So 1 bit shifted over 1 is 2, so that's like 2 to the first. If we bit shift it over again, that's 4, and then 8, 16. So it's a really fast way. Bit shifting, it only takes, I think, 1 instruction cycle on most architectures. So this will happen very quickly. Okay, so now we're gonna do our very first reduction, which is just taking the remaining everything past the largest power of 2 and putting that into the front. So we'll say if it's less than the largest power of 2. Oh, no, that's not what we want to do. We want to do size minus. So if it's 10 and we have 8, we're just taking the last 2. So that'll just be 10 minus 8, which is 2. And we're going to put it in the first 2. And we're going to take the first 2 that are after the largest power of 2 in our index. So we'll just say in IDX equals in IDX. Wow, this autocomplete's really good. Saves me some typing. I'm using the tab 9 one. I haven't tried GitHub Copilot, so let me know if that's good or not. Okay, we've got our... I'm opening AutoCAD, there's a little error. Okay, I'm pulling up my notes. We're gonna do a loop here, so we're gonna unroll it. Hopefully, if the compiler decides that's a good idea. Pragma unroll is just it's a hint. It's not required of the compiler. So for int I equals the amount of loops we'll have to do is just however much we shifted it over. So let me think here. So we have our largest power of 2. What I'm going to do is bit shift it over 1 each time. The first one we skip, like, so if in our example, if there's 10 and there's 8, if we have 10 elements that we're summing, and there's 8 being the largest power of 2. We'll skip actually the number 8. Our first thing will be to take because we've already done it here. Our first task in our for loop is to take the last 4 and put them into the first 4. So we'll divide this by 2. We went I greater than 0. So when there's 1 left, it does that very last one for us. And we will just bit shift it over 1. So it's important to remember to have this equal sign here so that I is operated on. So if IDX is less than I, we'll say in so first this will be 4, I will be 4. So if it's less than 4, we'll have 0 through 3 here, 0 through 3 here, and then 0 through 3 plus 4. That's perfect. And this will do it for us. That's our sum in place. CLZ takes an int, so let's use int here. We're not going to have any sizes that exceed the limit of int, which is over 2 billion. This should do it. So after we sum them, we need to synchronize. So we take the first 4, add the last 4 to it, and now before we start adding the first 2 and second 2 elements, we've got to make sure that the operation's done. So we sync across the grid. Okay, so here's our test. So we're going to test this now. Reduce test. If IDX is greater than or equal to size, we return out of here. Neural net float pointer. See, this is a problem with my long pauses. I like rereading my old code, not remembering it. This is void now. Result. We have a local register now, so we just sum in place here. And our result equals our GPU test data 0. Here we're adding a bunch of 1s together. So our result should equal size. So we have our main function. We'll do a cooperative run. Right here, we're just taking with our very first index, so our thread 0, we're just adding 1 over and over. GPU test data, which is a neural net float. Let me check how I'm doing my neural net floats. Okay, right now we're just using halves. Okay, so that'll do. All right, let's see it. Oh, we're doing the test. Test all equals 1. We'll come to CMake. And here we go. So counting the leading zeros gives us the highest power of 2. Well, gives us a log, which we can then just get the power of 2 out of really quickly. Because what we're looking for, all powers of 2 in binary is 1 followed by a bunch of zeros. So we just count how many zeros we're going into the number. On our 32-bit number, we take 31 and subtract that. And that gives us how many zeros are after it. So if we have 10 in binary is 1010, 8 is 1000. Our highest power of 2 is always just going to be 1 followed by zeros. The same leading 1 position, except all followed by zeros. So we remove all the 1s after that leading 1, and that's our highest power of 2. MNIST test. Let's see, our issue is we wrote to CSV. Oh, we didn't run number 6. We run number 6 for our test. My bad. Thinking of upgrading my processor. I have an AM5 or an AM4 slot. I have the AMD 2700, but I could get like a 5950 in there. I have the 2700 8-core, 3.2 gigahertz. For just $200 I could double my CPU speed. Okay, what is this error here? Convert half to float is not being found. And what is this being called in? File writer, which we don't need for our test. Okay, so we'll take file writer out from test. It does go in MNIST, I think. In test all, we don't need it, so. Okay, so it won't be needing that then. Okay, I'll be back in a second. Self-presence. I got some clamps to make my room really blacked out. That'll help the stream. Okay, here we have test all begin and end. We don't have an output. So let's check why that is. Test all, cooperative kernel launch, reduce test flock size. We should be printing here out of IDX0. Why wouldn't we be printing? Oh, we're calling the new keyword. This is only making data in our one thread. It's only putting the pointer in one thread. It's undefined for all the other threads. So I don't know. I should have done that last time. So let's do it the proper way. And do I have my CUDA check included? CUDA helper. No. Here is my CUDA error check. So I'll include this file. This is all on GitHub, by the way, so you can get this. This is a utility for, it reads the CUDA error. So here we have CUDA check, calls CUDA check expanded, which is this function. We get the result in for the first thing, and then the name of the function, and then the file name and line number with these compiler keywords and functionality here. So CUDA check expanded calls return error string if there is a result, and then it tells us exactly what our problem is. This might not work depending on what version of CUDA you have, but if it doesn't work, you can just remove the cases. So for instance, like earlier versions of CUDA, they don't have some of the, I think, like, I don't remember exactly, but some of these are not available in the in earlier CUDAs. So I don't think it's an architecture thing. I think it's your version of CUDA. I'm on 12.1. Okay, so we include this now, and I can call CUDA check on all of the CUDA intrinsics. So first, I want to allocate my half float array here. So I don't know if I can use half on CPU code. We'll try it. So we'll alloc here, and then we'll do size of neural net float. Times our size. And it's a dynamic allocation, so we can use predefined values. Okay, we'll have to cast it to void pointer. Oh, and we need the address that points to this pointer. Actually, I don't think we have to do this if we get the a reference to it. And then we're gonna change our function to take in this value. So it's gonna take in GPU test data. We'll cast this as void pointer. Do we need a reference to it? Because we're getting a reference to size. Yeah, I think we do. Kernel arguments is passed in as a list of void pointers, or an array of void pointers. Now in our reduce test, we'll take in our float pointer GPU test data. So we won't have to allocate it here, but to allocate it there. And we'll use our first thread to populate it with ones. It's float to half. We can't actually directly put in a half value. We have to do float to half for this. I hope the compiler optimizes that. Sum in place, we've got our data now. Our result is the first value. And so once we make a register and we assign it to this global memory value, all of our threads will have the same value in it in that register location, which is local to each thread. Okay, so if IDX is 0, we'll print, and we'll print if it's right, and otherwise not. We'll print this. We don't need to delete it here. We can free it after here. So CUDA check, CUDA free. And for this, we don't pass a reference, we pass the pointer itself. So let's give that a shot. Oh, and then make sure CUDA error checks there. It is. Okay, so we haven't changed anything in the CMake, so we don't need to run CMake again. This script will just build and run it without having to configure the project. And since we haven't added any new files, we can just do that. So this will build a bit faster. I was talking on mute the whole time. We have CUDA check sync here, which in debug mode, it'll device synchronize for us so we can see if there's any errors in the CUDA kernel that we just ran. So I'll run this after every kernel I run in case we go get an out of bounds error, something like that. And in release mode, it just does nothing, so the code will run a lot faster. That's not gonna fix this issue though. I'll give it a shot. And yeah, I am streaming from this computer behind me. It works way better than my laptop. I got some long cables running. So yeah, please tell me if it starts to light on fire or anything. Okay, we're still not getting our result printed out here. Let me look through my notes. So here we have our sum in place that puts our sum into this value. We'll always have IDX0 running. It should be printing either way. I don't know. While I think about this, let's fix this libcmt error. I found out for that there's a cmake command we can use to just not use libcmt as a default library. And that's this one here, set cmake linker flags, no default lib. Okay, so let's see if that, so we'll have to run cmake again, so I have to build it the long way with script 6. If this doesn't work, it's not working. So let's just try to, we'll print anything here. Anything, something we want. IDX, %D. We'll just print our index. I didn't need to run script 6 again, I can run script 7. But yeah, that took care of our warnings, so we've got no warnings and no errors for compilation. So when this code works, we'll be in good shape. Nothing's printing here. This is from reduce test. Is num of blocks correct? So we should always have at least one block. So this is correct. What could this issue be? What if I get rid of this? Yeah, I want to get that faster processor. It's only $200, then I can compile faster. Like twice as fast. Let's see this. If I even get the 5700. Still not printing here. Okay, well let's fix this first. If IDX is greater than or equal to size, and by size I'm passing in 10, maybe it has to do with these pointer values. So we have the reference here. Size is 100. Is it because I can't do this? I know the size of the neural net float is 2. Can the CPU not read this? It ends in CU here, so I think the file name ends in CU, so I think NVCC comes through and makes this all readable by the CPU compiler. It's not printing the. What if is it this sync here? It's gotta be. We're setting float to half. We're dereferencing a half here. Okay, so I'm gonna take out the cooperative groups. We can run script 7 here. And now this is a extremely basic kernel. We should just see 0 to 100 print out now. It's no longer cooperative, so I should be able to just run it like a normal kernel. One block with 256 threads. We'll give it GPU test data and size. We need 3 right brackets, angled brackets. Okay, we got a warning about kernel arguments. That's fine. Still not running, so I'm malicking. If I get, and we're passing in 100 for size. Int. Block size. So the first one is the number of blocks. Second here is block size. What if I print it before we return? That can't fix it. Print F. Do I have Studio? Yeah. Okay. This is printing. Okay, so I'll just synchronize it here for sure. What? I'll try re-typing neural net float to regular float. Okay, what if I don't put all these threads to sleep? This is a brain buster. Test off again, test all end. This should be catching our errors. Let me make sure this is in debug mode. Type equals debug, yes. Let me go to the file. If I just run test all, yeah, it's not printing anything. What if I use the command prompt? Copy that, go to the command prompt. It's not working. This is the most basic kernel. Print 5. No end line. Just to make it even easier. Go to the right directory. What is going on? Is my GPU on? Here's my GPU. GPU's turned on. The most basic kernel possible. If you guys know anything, I'm all ears. I guess I'll just try C making it again. Did I put in like a command? Stop working command? Oh, it's the wrong architecture. This is my laptop's architecture. It's 16 series. I'm on a 10 series. This might be the issue. Let's see what happens. Okay, 61 is the 1080 Ti. Alright, and I have to re-C make it now. That's my roommate. That's the problem this whole time. Wrong architecture. Okay, let's get this where it's supposed to be. Cooperative kernel. Okay, we're setting these all to 1. And now we run it. No CMake this time. Oh, this isn't gonna work because I changed it on that float to a float. It's half now. Okay, here we go. Boom. Oh yeah, it's passing. Pass, fast, pass. With the value of 100, adding up 100. Okay. So it works. Sweet. Now let's test it with a bunch of other values. Void summation test int size. Let's put in like the. Let's put in a multiplier because right now it's just 1. That's all we need. I'm pretty sure. Okay, so we'll have size here. We can do all this in the function. So we'll just set our size. It comes in automatically. Multiplier. We'll add in a new argument for that. Void pointer. Multiplier. Not void, void. That's all we needed. Yeah, then we'll pass in an actual multiplier. Oh, we need to reference multiplier. We'll just do float. Float pointer multiplier. We'll passing in an actual float. So this will be float to half multiplier. Let's see, we have sides in here properly everywhere. Yeah, looks good. Okay, so summation test. We'll do 100 and let's try 17.f. We'll do tons of stuff. Okay, 5. We'll go up by powers of 2. 16, 32, 64. Actually, for all these, we can just do 1 to the power of 1. So we can start with 1, which is 1 bit shifted 0 times. Oops, not settings. Okay, I have all these selected. I have this really cool extension, insert sequence. So first parameter is you say where it starts. Starts at 0, goes up by 1, and right aligned. Yeah, let's right align it. No 0 padding. Okay, so we'll go up through these powers of 2. And then we'll go up by powers of 10. Just because of the way this math is, it might pass with powers of 2 easier than powers of 10. These are all 17s. Let's do like a for loop. For loop. Let's do int. Okay, so we'll just have our multiplier here. Float multiplier. let's do like 10.f plus 5.f times I. So it'll be 10, 15, 20. And then these can all just be multiplier. And same with these. Multiplier. Oh, and we have to check that it's right. If result equals float. Well, just size times multiplier. And let's make this vibrant. Pass. Fail. You want it to really stand up. Upside down question mark. No, exclamation. Actually, CUDA probably doesn't support that. Okay, fail. We'll say, we'll point the values. Let's see. Size is %d multiplier %f size multiplier. Same thing here. We'll do an expected result. Expected result equals well, our result is half. Reduce test, excellent. Excelente. I think we just use float. So our actual result is half to float result if expected result equals actual result. And then we'll do actual result. Actual result yes. Okay. Now to here. All right, let's see what we get. Let's see if this even works. Oh, we got some fails. So at 10,000 with a multiplier of 10. Why do we have a new line there? Okay, yeah, that's why I didn't copy that. Okay, let me run this again. And we don't need these crazy long floats. Let's just do normal size floats. 2.2 F. Normal precision floats here. We'll make the width of this 6 for our integers. So we fail at 10,000 with a multiplier of 10. Let's see, what's our actual result? Infinity. We're expecting 15, and it's not going past 10,000. It should be doing that. Result infinity. Oh, how am I running this? Num block size. Let's see if I do. Why would it be passing? It passes all of the powers of 2. No, it only goes to 1024, which is, let's see, 2, 4, 8, 16, 32, 64, 128, 286, 512. 1024 is 10. How far are we testing to? Yeah, we're only going to 10. 12, 13. I have a feeling it'll actually pass higher with powers of 2. Yeah, it doesn't fail until 8,000. So here we have 10,000 failing. 1,000 is not. Let's see how high we get. Let's see, 4, 5, 8. We'll throw 2 in there. And let's line up our pass and fails. Okay, fail 819. We fail at 5,000. I know how to solve this. You know, let's try this with full precision. So we'll go here. Where we type def half neural net float. Let's see. If defined neural net full float, we'll use float for this. And here we'll do if defined neural net half float. And if we'll type def it like this. Okay, so the reason I'm doing that is we can't use these if it's full float. You saw earlier I had that compile error from that. So instead of doing float to half, I can do something like use float. And do float to half. Oh, so I'll do a macro. So we'll say define or define use float x as half to float, just normal float x. And then for our float, when we use float, it's just x. So we want it to be, we want to convert it to float here. Or actually, no, you know what? We'll make this name make full precision. This will be make full precision. Okay, so we'll put this in here. Make full precision is nothing. Use float will be, if we want to use float would be, maybe there's a better name for this, but we're putting a number like 1.f and we're going to make that a float. So that would be float to half. Float to half. So we could say make neural net precision. Yeah, that's a good name. Make neural net precision. And then if we put in a float for this and to make neural net precision, we don't have to do anything. Because it's a float. So float to half. Yeah, that'll do it. Get rid of that, and now let's add in our defines for CMake. So we'll say if neural net half float, and if, and then we'll just compile. And if we don't specify it directly, so we'll do else statement here, else statement, then we'll do full float. Let's print out a message, grab a message line. Using half precision floating point for neural network. And here we'll say use full precision. And we should put messages in here. Okay. Not using an activation function. Whoa. Here we'll put in using the Mick ReLU activation function. Let's see, and just so we don't have that problem again where the architecture is wrong, I have my Jetson Orin, which is an 87, I think. Let me double check. Let's see, it's on the wiki page. Orin, whoa. Man, it's just there. I could have saw it. You can do it. Oh, my internet. Oh, shit. Internet's not doing good. Okay, I'll just finish this up. Okay, I'm pretty sure it's 87. I'm gonna push this in case my internet cuts out. Created summation test. Adding support for full precision. Parameters. All right, I'll continue this. Let me check my phone. I'll use my phone's internet to see if this stream is working. My internet's got really slow. Happens sometimes. Let me see here. All right, internet's still working. Okay, but it's kind of failing, so I'm trying to wrap this up quick. Okay, so we'll use full precision first here. I know I don't have to put this in because it's in the else statement, but I'm just putting it in for notes. Oh no, full float. Okay. Okay, reduce test. This will be float to half, so use neural net precision. And I do have my float here somewhere. My float definition. Make neural net precision. And this one will be make full precision. Okay. Now let's test it out. Now that we're using, I'll have to update my, I'll have to run CMake now that I've updated CMake. And that's in build script 6. Let's see, come on. Come on. Gravity needs some new shoes. We made a lot of changes here, so. Oh wow, on full day, look at that. Oh, I got to 10,000, but it doesn't even print the numbers above that. Let's see, because I do go above 10,000. Yeah, I go all the way to 10 million. Okay. And that's where we're at. So let's see if our half precision works. Half float. Re-C make it. Oh, we're getting all this attention. Okay, so we get up to 5,000. If we do 4095. This one fails at 5,000, passes at 4,000, fails at 4096. Okay, we don't have to C make again. What's concerning too is that the fails are infinity. I don't see why that would be the case. Let's see. How high can... Let's ask ChatGPT how high half precision floats can go up to in full numbers. I've got ChatGPT 4. Okay, let's just look up the mantis. Oh, everything's gonna be frozen. Let's see. Mantissa size half float. Oh, exponent size half float. Oh, too slow. $40.95 fails. So we'll say up to 4,000. I know how to fix this. We'll rename the function sum in place up to 4,000 elements. Perfect. Now it works exactly as intended. Alright guys, so I'll look into this, see what the problem is, and we'll have to sum up more than 4,000. Well, we're doing this, so if we have any layer with more than 4,000 neurons, then we'll need this to work. That's the place we'll be using it, or that's the parameter that's going to go in, is the number of neurons in the layer. 4,000 is not going to cut it. It's too low. So there might be some other things we can do, and I'll check it out. But all right, thanks guys. Have a good one.